In this video we're going to look at the initial rates method for determining the order of different reactants. So just to recap very quickly, last video we looked at the continuous monitoring method, which is when you measure the concentration over time. Now again, we very rarely actually measure concentration over time. We measure something that is proportional to concentration over time, perhaps volume or change in mass. Things like that. But you can plot a concentration time graph, and from your concentration time graph, by calculating the gradient of the line, if you have a curve, then you need to take tangents and calculate the gradient at particular concentrations, and then plot your results as rate concentration graphs. You can then very clearly see what order the reactant is. So if the rate does not change with concentration, then it is zero order. If there is a directly proportional change with rate and concentration, then it is first order. And if there's an exponential change between the rate and change in concentration, then it is second order. So what we're going to look at today is the initial rates method. Okay, an alternative method, but has the same outcome. You're able to determine whether a reactant is first, second, or zero order. So in this method, rather than with continuous monitoring, where you run the experiment from start to finish and work out the concentration at different times, here you're going to run a reaction and calculate the initial rate of that reaction, and then you repeat it with varying concentrations of your reactants. And then what you're able to then do is compile a table showing the different concentrations that you've used and the initial rate of reaction. And you'll be able to therefore see the effect of changing the concentration of your reactant has on your initial rate, and therefore you can deduce whether it is zero, first or second order. So again, just to reiterate, if a reactant is zero order, then changing its concentration will have no effect on the initial rate. So the change in rate is equal to the change in concentration to the power 0, which essentially makes it 1, so the rate doesn't change. If a reactant is first order, then changing the concentration will have a directly proportional effect on the initial rate, so change in rate will be proportional to the change in concentration. So if you double the concentration, you'll double the rate. If you halve the concentration, you will halve the rate. And finally, if a reactant is second order, then changing the concentration will have an exponential effect on the initial rate. So rate will increase by changing concentration squared. So you would get an exponential increase in rate. So if I doubled the concentration, it would quadruple the rate. If I halved the concentration, it would quarter the rate. So the kind of questions you're going to be asked are going to look a lot like this, where you have a table of data and they are showing a reaction. So here we have 2A plus B goes to 2C and D. Now they are the same reaction. Each row here is a repeat of the same reaction with different concentrations of your reactants A and B. So this is experiment 1, 2, 3. And they've just repeated it with different concentrations and recorded the initial rate of each one of these. So what we need to do, and the easiest thing to do, is try and find two experiments where one of the reactants remains the same and the other one changes. So I'm going to look at experiments 1 and 2. So between experiments 1 and 2, they didn't change the concentration of B, because remember we're not isolating the one reactant. The rate of reaction is determined by all of the reactants, so you can't possibly compare them if more than one of them is changing, okay, unless you already know the order of that reactant, which you're going to come to in a little bit. So no change in B, but A has doubled. Okay, so B didn't change, A doubled. What effect did this have on the rate? It doubled it. So if the concentration of A doubles, the rate doubles. So what does that tell us about A? It tells us that A is first order. So concentration of A is first order. because doubling concentration doubles the rate. So directly proportional response. So A is first order. So let's have a look at B. So in order to work out the order of B, we need to find two experiments where A doesn't change. And I'm going to go with 1 and 3, because in experiments 1 and 3, A does not change, but B doubles. And what happens to the rate between 1 and 3? It quadruples. So if doubling the rate quadruples if doubling the concentration quadruples the rate, then the difference, the change, is proportional to the change in concentration squared. 2 squared is 4. So B must be second order. Because doubling the concentration quadruples the rate. Okay, so now we know that A is first order, B is second order, and finally the overall order of the reaction is just the sum of the orders of the reactants. So 1 plus 2 is 3. So the overall reaction is a third order reaction. And what that means is, if you were to double the concentration of A and B, then the rate would increase by 2 cubed in total. Okay. So for the reaction here, nitrogen oxide and hydrogen go into nitric oxide and water. The following rate data were collected. So we're going to do the exact same thing. We're going to look for two experiments where one of our reactants stays the same but the other one changes. So we've got experiments 1, 2, 3. So I'm going to start again with experiments 1 and 2 because the hydrogen doesn't change, but the nitrogen oxide has doubled. And what effect has that had on our initial rate? Our initial rate has increased by a factor of 4. Again, the rate increased by the change in concentration squared, so that tells us that the nitrogen oxide is second order. Because doubling concentration quadruples the rate. Right, now let's look at the hydrogen. So we need two experiments where the nitrogen oxide stay the same. So I would say experiments 2 and 3 because it has not changed. And the hydrogen has doubled. What effect has that had on the rate? It's had no effect. So if change in concentration has no effect on the rate, it is a zero order reactant. So hydrogen is zero order because changing concentration has no effect on rate. So the overall order is second, 2 plus 0. Here we have the reaction between PCl3 and Cl2, creating PCl5. So again, we're going to go through the same method. We're going to look for two experiments where one of the reactants stays the same, but the other one changes. So 1 and 2 seem like the obvious choice because PCl3 does not change, but the Cl2 has halved. and the effect that has had on the rate is that the rate has quartered. So straight away we can say that the Cl2 is second order, because halving concentration quarters the rate. But when it comes to the PCl3, now what we don't have here is we don't have two experiments where the Cl2 has stayed the same. But we don't need to know that, because we already have established that the Cl2 is second order, which means that we can take into account the effect of the changing concentration of the Cl2 and still work out the initial rate, what the initial rate should be from that change in Cl2, and then work out the effect the PCl3 must have had upon it. So when you're in a situation like this, what you should do is look at the reactant that you already know the order of. So let's have a look. It's gone from 1.26 to 2.52, so it's doubled. So it's a second order reactant, which means that if I double the concentration, it will quadruple the rate. So it should go from 6 times 10 to the minus 4, should increase by a factor of 4. So it should increase to 2.4 times 10 to the minus 3. I'm just going to write that in here. So that is the initial rate. So if we ignore the PCl3 for now, if I'd doubled the Cl2, which is what I have between experiments 1 and 3, then the rate would increase from 6 times 10 to the minus 4 to 2.4 times 10 to the minus 3, an increase of a factor of 4. And we know that's going to happen because we've already established its second order. So in terms of the PCl3 then, well, what's happened to the PCl3 between 1 and 3? Well, it's doubled. And what is the difference between this rate that we've calculated from changing the Cl2 and the actual final rate? Well, it's exactly double, isn't it? So by doubling the PCl3, it has doubled the initial rate. So it's first order. Because doubling concentration doubles rate. So the overall order of this reaction, you've got a second order and a first order, so the overall order is third order. And finally then, two compounds X and Y are known to undergo this reaction. So we're going to look, we've got lots of different experiments here. It doesn't make any difference if you've got 2, 3 or 5 experiments. The same method applies. So I'm going to look at 1 and 2 because X doesn't change, but Y doubles. And what effect does that have on our rate? Well, within reason, it increases by 4. I think it increases by 3.99, but we can all agree that that's as close enough to 4. So by increasing Y by a factor of 2, it's increased the rate by a factor of 4. So Y is second order because doubling concentration quadruples rate. So doubling the concentration quadruples the rate. And then for the X, so we need to find 2 where the Y concentration doesn't change. So I'm going to use experiments 1 and 4 because Y doesn't change, but the X doubles. And what effect has that had on the rate? Well, it is basically doubled. So we could say that X is first order
because doubling concentration doubles rate. So we've got a second order and a first order reactant, so the overall order is third.